Namaskar, my name is Priyanka Shandilde and I'm going to discuss about silicate structures. Silicates are most abundant rock forming minerals, and in this presentation I'll be discussing about the various structures which silicate minerals form. And I'm working as an assistant professor at Government College Narnaul, and this presentation has been prepared under the aegis of Directorate of Higher Education Haryana. So let's get started. As I told in my previous video that there are different categories of minerals like oxides, sulfides, carbonates, and silicates, native elements, so on. And these are called the Dana mineral classes. And out of these, most of the minerals are the silicates, which constitute 92% of Earth's crust. Because SiO4 is not electronically neutral, silicon is 4 positive, oxygen is 2 negative, so there is net 4 negative charge over SiO4, and that's why it tends to combine with other elements like cations to make a neutral species. So, the basic unit or the building block of silicate minerals is silicon tetrahedron. The basic unit is SiO4 4 negative, and the structural representation of the silicon tetrahedron is such as that the four oxygens are at the corners of tetrahedron, and there is one silicon which is at the center of the tetrahedron. Because silicon and oxygen are two major elements and of earth crust, so the resultant silicate minerals are also most abundant within the earth crust and mantle. The variety of silicate minerals is produced by the linking of silicon tetrahedron with the another silicon tetrahedron by sharing oxygens. So depending upon how many oxygen one particular tetrahedron share with the another, there are various structures listed under the category of silicate structures. Let's see. So the as I told, basic it can be represented by the tetrahedron or by drawing some atoms which where this orange ball represent silicon which is at the center, and these are four oxygens which are at the corners. Likewise, we can see the three oxygen atoms here, and this one is the oxygen atoms which covers silicon. Silicon is in the interstitial space of a space between oxygens. Okay, and this one is the geometric representation of tetrahedron. So, as I told, that depending upon how many oxygen one tetrahedron share with the another tetrahedron, there are various categories of silicate structures, which are of 6 types: Neso silicates, soro silicates, cyclo silicates, silicates, phyallo, and tectosilicates. So, we'll discuss them one by one. Okay, so nesosilicates. These are also called orthosilicates. What happens in nesosilicates? Silicon tetrahedron is isolated tetrahedron, means there is no sharing of oxygen with another tetrahedron. So these are bounded to one another by ionic bonds with interstitial cations, means two tetrahedron are not linked directly, but there are atoms cations in between by which they are bounded. The ratio of oxygen and silicon is 1:4 in this packing. The packing is dense, so the density of these the minerals which are nesosilicates is high, and there are tetrahedrals which are independent, and there is very low substitution of aluminium at the site of silicon, and many nesosilicates, but not all, have orthogonal crystallographic systems. That's why these are called orthosilicates. Because we all know that there are 6 crystal systems: cubic 2, triclinic, and there is one more which is called orthorhombic. Okay, so orthorhombic represent most of the minerals of nesosilicates. Okay, the one example of nesosilicate is olivine. So we can see the isolated tetrahedra here, and the green dots are the cations in between, which are responsible to bound them, right? Okay, so again olivine, this is the single tetrahedron, and this is the mineral olivine, which has the structure of nesosilicates, and this is a green mineral olivine. So next category is sorosilicates, which is also known as disilicates, because there are two tetrahedra joined together through one oxygen, right? This is one, this is second, and these are joined by sharing one oxygen, right? The silicon oxygen ratio would be 2 raised to 7, because two silicons are there. One is within this tetrahedron, one is within this tetrahedron, two, and the number of oxygens are 1, 2, 3, 4, 5, 6, 7. So the ratio is 2 raised to 7. If we talk about the silicon oxygen ratio in olivine, we'll see that here we have one silicon at the center and four oxygen. So ratio is 1 raised to 4. Okay. So these commonly form edge sharing linked octahedral chains, and the example is epidote, because this link where only one oxygen is shared between the uh, tetrahedra. So the bonds between chains and within sheets are quite strong. Large coordination spaces that accept large cations, which is in between two tetrahedra, right? But the bonds between sheets are weak, leading to the common phenomena of only one direction of perfect cleavage. That means one sheet where so many tetrahedra are arranged are linked with the cations, then another line of tetrahedron. So in between the sheets, the bond is weak, because of which they can be a cleavage plane. Okay. So the example is epidote. We can see the ratio is 2 raised to 7. Okay, so next structure is cyclosilicates, which is also known as ring silicates. They can be rings of 3, 4, 6, 8, 9, or 12 membered of Si4 positive tetrahedra. So 6 membered are the most common silicate structures. Okay. So silicon oxygen ratio is 1 raised to 3. The high concentration of strongly linked bonds yield relatively dense minerals that are quite hard. Example is beryl. Beryl is one of the gems which is very popular. So we'll see the structure. This is a three-membered ring and this is a six-membered ring. Okay, but the ratio of silicon and oxygen is same whether it is three-membered or six-membered ring. Right. So here we can see with three silicon, 9 oxygens are there. So ratio is 1 is to 3. And here we can see that with 6 silicons, 18 oxygens are there. So the ratio is 1 is to 3 only. But there are some negative charges which need to be balanced and which can be balanced by the cations. Okay, so if we compare the cyclosilicate with the next category, which is the phyllosilicate shade structure, so the distinction is there will be a single ring, while in sheet structure there will be the repetition of rings with, where more number of oxygens will be shared. While in case only one tetrahedron is sharing two of its oxygens, while in case of a sheet structure, one tetrahedron is sharing three of its oxygens. Okay. So this one is cyclosilicate, this one is the phyllosilicates, which we will discuss later. Right. So next category from cyclosilicates to inosilicates, from ring to chain. Okay. So within this category we have uh, two divisions. One is single chain, another one is double chain. So the most important two mineral groups are the pyroxenes and amphiboles, where pyroxene belongs to single chain structure and amphibole to double chain structure. So this mineral is pyroxene, which is a dominant mineral of igneous rocks and metamorphic rocks. And here we have the chain structure, single chain structure, and we can see the ratio of silicon oxygen is 1:3. So if we count number of so let's take example of the chain up to here, right, and this one. So within 3 silicon, how many oxygens do we have? We have half of this oxygen and half of this oxygen, one, right? 1, 2, 3, 4, 5, 6, 7, 8 and 9, right? So with 3 oxygens we have with 3 silicons we have 9 oxygen. So 3:9 means ratio is 1:3. Okay. So next one is amphiboles. In amphibole, this is the black colored mineral is amphibole, which is also a common mineral of igneous and metamorphic rocks. And the ratio with 4 silicon, there will be 11 oxygens. So while counting, we'll take care of the oxygen which is being shared within the chain. So this will be counted as half, this will be counted as half. So if we take into consideration this ring, so these 2 oxygens will be considered as half as well as these 2 oxygens. So the ratio would be 4:11. Right. In case of phyllosilicates, which is also known as the sheet silicates, right? So if we go back to amphiboles and pyroxenes, we can see that there are some weak planes, and weak planes would be because of the strong bond along these chains and the weak bond within the chains. So there will be a weak plane, and where there can be cleavage planes, right? Same in case of amphiboles. So within the double chain, the bond is strong, but within the within the two double chains, the strong would not be that much strong. So there will be weak planes of cleavages. So next category is phyllosilicates, which are known as sheet structure. So within sheet structure, we can say that there are tetrahedra which are sharing their 3 oxygens with another tetrahedron. Only one oxygen is left out. So this oxygen is not being shared by any of the tetrahedra, and so minerals which are formed by the sheet structures will have cleavage plane, basal cleavage plane, and so within the sheet the bond is strong, but intersheets means between 2 sheets the bond will not be that much stronger, so they will be weak plane, right? So in phyllosilicates, the ratio of silicon oxygen will be 2:5, and the most common minerals which are sheets silicates are mica and included muscovite, biotite. The form we can see in formula also Si3 and Al, where aluminium is replacing one of the silicon side. So there will be 4:10 means 2:5. Okay. Some clay minerals also comes in this category like kaolinite and pyrophyllite. Pyrophyllite is mica only. So here this aluminium is replacing silicon, but these are at another lattices, another locations. Okay. Here also this is the aluminium which is at this site, and here no substitution of silicon, so ratio is 2:5. Here this aluminum site is different, while silicon oxygen are having ratio of 2:5. Here only one aluminum is replacing one silicon site, so there are actually 4 silicon, supposed to be 4 silicon, so ratio is maintained 4:10 and 2:5. Right. So these are the examples of sheet structure. We can see there are sheets of mica, and this one sheet can be removed from the another because the bond between 2 sheets is not that much strong and there is weak plane. So one vessel cleavage plane is developed in micas. Okay, so this is biotite and this is muscovite. So now, because we have talked about the Neso silicates, soro silicates, cyclo, ino, and now phyllosilicates, so we can say that slowly and gradually we are going towards the complex structures. So structure complexity is increasing and the number of sharing of oxygen is increasing. So quartz and feldspars are some of the most common framework. Framework silicates, which has a ratio of silicon and oxygen 1:2. Examples are albite, orthoclase, and orthite. So we can see that the structure is becoming more complex, and the ratio of silicon oxygen is 1:2, means most of the oxygens are shared by the tetrahedron, right? We'll see how it happens. So here with this silicon, the aluminum is replacing one of the silicon. So there are four silicon actually. So 4:8 means 1:2. In this case also 4:8, 1:2. In this case there are two aluminum replacing silicon. So 2 to 4, 4:8 means 1:2. So ratio is maintained. Okay. So tectosilicates, these are called framework silicates. So in case of framework silicates, we do have as I told, we are going towards the more complex structure and more polymerization, not depolymerization. Okay. So this should be polymerized. Okay. So tectosilicates, we do have silicon oxygen tetrahedron arrangements where most of the oxygen atoms are shared by the adjacent tetrahedron. So all oxygen atoms are shared and the ratio is 1:2. Quartz is useful as a source of silicon for silica. So it is used in electronics as an oscillator and as piezoelectric material. So the arrangement of tetrahedron would be like this only, and all the oxygens are being shared. We can see that this is upside down tetrahedron, and which is sharing its apex oxygen with the one which is at the base. So all the oxygens are being shared. So ratio is 1:2. Structure of feldspar. So two major minerals of this category are quartz and feldspar. Structure of feldspar is similar to SiO2 polymers as I told, but to neutralize the charges, there are some cations which are in between the complex structure of tetrahedra. Right. So minerals are rendered electrically neutral as a result of being stuck with alkali or alkali earth element cations. Right. So this is the arrangement of feldspar, and there are some cations in between, and this is the plagioclase feldspar, the in white color mineral, and here orange color mineral is K feldspar, which is in granite rock. Okay, so to summarize this presentation, I can say that there are six major silicate groups: sorosilicates, nesosilicates, cyclosilicate, ring structure, ino, phyllosilicates, tectosilicates. Okay, so from Neso to tectosilicates, these groups represent more polymerized structures from Neso to tecto. Okay, so Neso has isolated tetrahedron, while in tectosilicates the tetrahedra are linked with oxygens and by sharing all the oxygens. So the structure is more complex in tectosilicates compared to nesosilicate. So these are more polymerized structures in case of tecto. By depolymerized are in Neso. So there are multiple variations within each of these groups, leading to a variety of permutations for each. However, these are the major building blocks of all the silicate phases. And in addition to these, the non-silicates of which carbonates dominate, as I told in previous lecture also, carbonates include calcites, dolomite minerals, and okay. So while summarizing the structures, mesosilicate isolated, there are two tetrahedra which shares one oxygen and with ratio 2:7. In cyclosilicates, the ratio is 1:3, and two oxygens are being shared with the adjacent tetrahedron. And in case of inosilicates, the chain structure is followed, single chain and double chain. So in case of single chain, ratio is 1:3. Within this entirety, with two silicon, six oxygens are there. In inosilicate, within this ring, with four silicon, 11 oxygens are there. And in phyllosilicates, with two silicon, five oxygens are there. Okay, so in case of tectosilicates, the structure is more complex, and we do have ratio of 1:2. Right, so these are the references which I have taken the help of, and there are some diagrams and content and slides from these sites. And for further studies also, you can follow the links, and the links will be given in description also, and you can go through the links. Okay, so because I have summarized about the silicate structures, so there is a quiz to test whether you have understood the content of this presentation or not. And this is a very simple quiz, and hopefully you all can answer all the questions. There are 10 questions, including multiple choice as well as fill in the blanks. So the first question is, which one of the following is not a silicate mineral? So I have given so many examples within the types of silicate structures. So one of them is not there, and which is a different type of mineral, which can be any oxide, sulfide, sulfate, or carbonate, but other than silicate, right? So you need to find out that one mineral out of these four choices. Second question is, which is not one of the silicate structures? So I have given you a list of silicate structures. There are 6 of them. So you need to find out which one of these 4 is not a silicate structure, right? The third question is, what is the ratio of silicon oxygen in mesosilicates? Okay, so out of this, one would be the right answer. And which of the following minerals has the most complex structure? Whether it is apidot, olivine, quartz, or serpentine. So first you need to figure it out whether which one is a nesosilicate, which one is tectosilicate. Then you can answer whether one of them has complex structure or not. Okay, so next question is, mention the name of one sheath silicate. So I have given so many examples of minerals within the particular silicate structure. So which one of them is a sheath silicate? Okay, next question is, which of the silicate structures has isolated tetrahedra and bounded to one another by ionic bonds with interstitial cations? Isolated tetrahedra, so you can easily answer because one of the silicates has the isolated tetrahedra. Okay, next question is, dash is the basic unit of silicate minerals, right? You all know olivine crystallizes in what crystal system? Cleavage plane is dash in quartz mineral. Okay, so I have given answer here only. Cleavage plane is absent in quartz mineral. Okay, sorry for that. So next question is, the silicon oxygen ratio in tectosilicates is. So you can figure it out. Okay, so that was all about the silicate structures. Hopefully you enjoyed the video, and thank you so much for listening. This is my contact detail. If you have any doubt, you can write me on this email ID. I'll try to answer you. Thank you. Thank you so much.